Acid-base models, such as the three common ones, the first two we've discussed in first-year chemistry, Arrhenius' acids and bases, Bronsted-Lowry's, but the new concept introduced in AP Chem is Lewis acids and bases. The concept of which of these three definitions is the broadest versus the narrowest is something that is always easiest to relate to in terms of a mathematical diagram called the Venn diagram. If you look at this diagram, can you identify which of the three acids is the most broad, the most all-inclusive acid and base definition? Hopefully you had the correct conclusion that Arrhenius is a pretty narrow definition of an acid and base, a substance that produces hydrogen ions or hydroxide ions. A little bit broader definition with the Bronsted-Lowry, and then finally the most broad definition of them all is a Lewis acid and base. The lab that you just finished doing is a good example of a Lewis acid and base. And the thiocyanate ion has lone pairs on both the sulfur and the nitrogen, and it's the sulfur on the thiocyanate that serves as the electron pair donor to the iron +3 ions. And so this ion is called the electron pair donor, which according to the Lewis definition would make it a electron pair donor, which would be called a base. If you go back to this definition, that falls far outside of the concept of producing a hydrogen ion or a hydroxide ion. There is no proton to accept or donate. So something that is a Lewis acid or base may fall outside of the range of definitions of something that is a Bronsted-Lowry or Arrhenius. Conversely, if a substance is an Arrhenius acid or base, then it is also Bronsted-Lowry and a Lewis acid or base. To review a little bit about Bronsted-Lowry, the molecular diagram or models here show that the ammonia, represented here, serves as a proton acceptor. If you look at, on the product side, what ammonia has morphed into, it has morphed into or changed into an NH4 plus ion. So in going from ammonia NH3 to NH4, the substance has taken in a hydrogen ion, so it has accepted a proton. A proton acceptor is a base. Water serves as the proton donor, so water is serving as the Bronsted-Lowry acid. Arrhenius would not call water an acid or a base. So this is another example of how we can apply that concept of the Venn diagram. Another example of water. Water in this case is serving as a proton acceptor, which means that it is a base. So water can serve as both proton donor and proton acceptor. Thus the term amphoteric, meaning that it has the properties, water does, of being both an acid and a base. Ammonia is rarely going to act as an acid. I don't want you to be confused by this. Water has both properties, depending on its environment, of acting both as an acid or a base. Ammonia rarely would act as an acid. That would be under non-aqueous conditions, and that's beyond the scope of this class. If we look at the equilibrium constants of various strong and weak acids, what we can form a general conclusion about is the conjugate pair of both acids and bases. So if you take something like HCl, hydrochloric acid is a very strong acid, its conjugate base, do you know which one it is? Chloride ion. So the chloride ion is a relatively weak base. So if an acid is very strong, like HCl, its conjugate, chloride ion, is a very weak base. That means it is not able to readily accept a proton and form HCl. Being strong, it wants to completely dissociate and is present as the chloride ion and the hydrogen ion. Take the time to identify, just by way of review, the conjugate acid-base pairs that are shown on this slide. Pause it and put this on your homework notes to turn in to class. Where we're going to go from here is to a little bit of practice of writing equilibrium equations and the expression for both an acid and its conjugate base. So take a moment and write an equation that has acetic acid plus water on the reactant side. Write a similar equation using the acetate ion and water on the reactant side, writing the equilibrium constant expression for both the Ka for acetic acid and also the Kb. Pause the podcast and return in just a moment. Looking at the two equations, you can see that acetic acid, as you know, it's an acid. So the reason why it's an acid isn't really because it has a hydrogen ion. It's because it produces hydronium ions, and in doing so increases the concentration of the hydronium ions to be higher than the concentration of the hydroxide ions. So acetic acid is an acid because it raises the concentration of the hydronium ions. Here's the equilibrium constant expression. The value is 1.8 times 10 to the minus 5. The flip side is when the conjugate base interacts with water. Notice the similarities, but yes, the subtle differences between the equations for acetic acid versus its conjugate base. Acetic acid is an acid, but the acetate ion functions as a Bronsted-Lowry base because it has the ability to accept a proton. But what makes the solution basic is the formation of hydroxide ions. Increasing the hydroxide ion concentration makes the pH go up. And again, we have the equilibrium constant expression. Take the time to do a little bit of math and multiply Ka, this value here, by Kb, this value here. And also multiply the numerical value, 1.8 times 10 to the minus 5, by 5.6 times 10 to the minus 10. And what you will discover is that Ka times Kb equals Kw. So this expression for Ka multiplied by this, notice what terms drop out, and you're left with hydronium ion times hydroxide ion, and the value that it will equal will be 1 times 10 to the minus 14th. So if you're given Ka, you can calculate Kb, and vice versa. As with many equilibrium calculation problems, there's quite a variety of permutations that you can do for these problems. But common one is to, if you're given the Ka and the concentration of the solution, you can calculate the pH, and along with that, you can calculate the percent dissociation. Conversely, if you're given the concentration and the pH, you can calculate Ka. So these are just two examples that I'll be asking you to do in your problem solving for today. Two problems to calculate, one with a more concentrated 1 molar acetic acid, and the second one, 1/100th is concentrated. Go ahead and stop the podcast. Calculate a value, put it on loose leaf, of what is the concentration of the hydronium ion, and then from there you can calculate the pH. Remember that the setup is the ice table is exactly like we've been doing. The nice thing about acid-base chapter is that conveniently the coefficients are 1. So solving for x is much more simplified. If you look at this equation, however, you can see that it's set up for a quadratic. But the question to you is x going to be small relative to this value 1.0? And the answer is yes, it will be small, and yes, you can neglect this x. The reason being is that the concentration of this acid is more than 10 to the 4 times as large as the equilibrium constant. So when you go ahead and solve for x, the value of x is going to be extremely small. So in terms of sig figs, this difference here will end up being essentially 1.0 minus a number so small that you end up with 1.0. So that simplifies the problem. So you have x squared over 1 equals the equilibrium constant. Go ahead and calculate both the concentration of the hydronium ion, the pH, and the percent dissociated. And do the same thing with the more diluted acid. Again, can you use Le Chatelier's principle to make a prediction? The prediction will be, will the equilibrium shift to the product or the reactant side with the addition of water to dilute the solution? But the second question is, okay, so we know what the shift might do, but what impact does that have on the pH? More complicated problem than what we were doing in the last chapter. Two thought questions here. So if we have a concentrated acid, a liter of 1 molar HCl, and we dump in some salt, sodium chloride, will that affect the pH? Write down what your thinking is for that. Second problem to puzzle over is in the case of a weak acid, if you do the same thing, add some sodium acetate to a liter of 1.0 molar. The equilibrium is still the same, but now instead of starting with 0 products, we're starting with 1.0 molar. Oh, wait a minute, let me fix that. 1.0 here on the reactant side, and then this is the 0. Hydronium ion, likewise, down here. So, use Le Chatelier's principle, and I bet you could say, well, if I add some acetate ion, that's going to shift the equilibrium back towards the reactant side, so that's going to use up some hydronium ion, so there'll be less hydronium ion than there was in just pure 1 molar acetic acid. So adding acetate ion, we would think, would reduce the hydrogen ion, and if you reduce the hydrogen ion, it's less acidic, which would mean that the pH that you calculate in this example would go up. Make sure you do the calculations to verify that. Aniline is a weak base, and if you think about it, if you look carefully at the structure, it's similar to ammonia, NH3, except instead of 3 hydrogens on the aniline, one of them has been substituted for a hydrocarbon stuck on it. It's a base, and so as such, it functions as a proton acceptor. And ammonia has a lone pair of electrons, and that's part of the reason why it's a good proton acceptor. So write the equation of aniline accepting a proton. What will the conjugate acid of aniline be? Write that equation and then move forward and calculate and bring your answer into class tomorrow. The pH of 2.0 molar aniline solution if you have a Kb of 3.8 times 10 to the minus 10. Remember that since it's a base and the solution is basic, what you're going to be calculating is the concentration of the hydroxide ions. So we know that the pH is going to be above 7. So don't just calculate. Think about what you're doing when you're working through this answer. So in your work at this point in time in the chapter, you should be pretty well through doing problems all the way through, but not including polyprotic acids. So that's about halfway through this chapter. I'll pick up a few more details in class.